Hello, Honors Geometry. Remember, in these videos, I want you to be taking notes. I will be going fast, so if you need to slow down, please feel free to pause the video, rewind, or go back to anything you need to. And if you have any questions about anything I say, I would make a note of that as well in your notes, so you can ask that in class. All right, in this video, we're going to be talking about perpendicular bisectors and angle bisectors. So a reminder about a perpendicular bisector. It is a segment or ray, line, or plane, and it has to be perpendicular to a segment at its midpoint. So notice that we have this segment AB. Its midpoint is point P. So C, the line CP, is what we call the perpendicular bisector. Notice that AP and PB are congruent to each other. Also, we have this other vocabulary term, equidistant. A point is equidistant from two figures if the point is the same distance from each figure. So when you hear that word, that's what that means. So here's our perpendicular bisector theorem. Right? In a plane, if we have a point on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. So notice that I have a point on this perpendicular bisector. That point is P. My perpendicular bisector is the line PC. And what we're saying is that point P is equidistant from the endpoints of the segment. All right, so endpoints are A and B. So AP is going to be the same distance as PB. That's what that is saying. All right, now the converse of that, if we know that there's some point, notice that we don't even have this labeled, so let's label this maybe point D. If I have some point that is equidistant from the two endpoints of the segment, all right, so I see that DB is congruent to DA, then I know that D has to be on this perpendicular bisector, even if it doesn't show that it's actually on it in the diagram. Okay, so D has to be on the perpendicular bisector PC. That's what the converse says. All right, so now we're going to apply this perpendicular bisector to a triangle. So here's just an example of what that looks like if I have a perpendicular bisector of a triangle. Notice that this is perpendicular, obviously, and it goes through the midpoint of this side. All right, so it doesn't necessarily go through the vertex or any special point anywhere else on that triangle. It just has to be through the midpoint and perpendicular. Now, concurrency, that means that when we have three or more lines, rays, or segments that intersect at the same point, we call that concurrent. And that point of intersection is what we call the point of concurrency. So since we're dealing with triangles, we are going to be looking at all three perpendicular bisectors of the sides of the triangle. So we're going to look at that point of concurrency. So the concurrency of perpendicular bisectors of a triangle, so that just means that if we draw all the perpendicular bisectors of a triangle, they're going to meet at what we call the circumcenter. So here are some examples. All right, so in this first triangle, you see we have all three of these perpendicular bisectors meeting, and notice that that point of concurrency is inside of the triangle. However, if you have a different kind of triangle, all the perpendicular bisectors, they could all meet on the triangle. Or in this figure, this last one over here, we could have that point of concurrency be outside of the triangle. And the reason we call this the circumcenter is because we can, this point of concurrency, the circumcenter, is the center of a circle that is circumscribed around that triangle. So if I draw a circle with this point, well, my center is a little off. Let me redo that. So if I draw, as that's the center of my circle, and again, where I drew my lines, it might have been off a little bit. All right, but that circle is going to touch all 3 points. So it should be touching right here, but all 3 points of that triangle. Okay, so that circle is circumscribed around it. Okay, maybe I'll have better luck with this one. Maybe this is drawn more accurately. Okay, so that one's not too bad. Maybe if I move it over a little bit. So yeah, that's a little better. So again, that is the center. The circumcenter is the center of that circle that is circumscribed around the triangle. Okay, so that is created when we have perpendicular bisectors. Remember, these blue lines are all perpendicular bisectors, so they are perpendicular and they bisect each of their sides that they intersect. Okay, so that's our perpendicular bisector's point of concurrency. All right, now what do we know about that? We know that the circumcenter is going to be equidistant from the vertices of the triangle. And if you think about it, that makes sense, doesn't it? If this is going to be the center of a circle, well, all of these, if I drew in the points to the vertices, those are all radii of that circle. So all of those are going to be congruent. All right, same thing if I did over here. If I drew that line, that line, that line. All of those are radii of that circle. So those are going to be congruent to each other. So this is the actual theorem, and it says just what we were talking about. So the perpendicular bisectors of a triangle intersect at a point. Here, that's point P. At a distance that is equidistant from the vertices of the triangle. So they're talking about these red lines here. All right, all of these are going to be the same distance. All right, and you can see that. Here's another way of saying that. All right, so moving on. Let's see if we can use this in a diagram. So if I have this diagram, and I want to find PS and QS. So PS is right here in green, and QS is this in blue. All right, what I want you to notice is that S, it says the perpendicular bisectors of this triangle meet at point S. So S is our circumcenter, which means that all of the lines to the vertices of the triangle, here are the vertices of the triangle, those should all be congruent. So this one, and this one should all be congruent. So all we have to do is figure out what is one of those in length. So SR is 10, so that means PS and QS both equal 10. All right, so moving on. Angle bisectors. So we've talked about angle bisectors and what those are. Remember that an angle is bisected if it creates two congruent angles, and that's done by a ray. So if a point is on the angle bisector of an angle, then it is equidistant from the two sides of the angle. So this is our theorem. So if I have a point that's on this angle bisector, notice this ray right here is our angle bisector. And that is going to show that these two distances, right here and right here, are congruent. And remember, what we mean by distance is perpendicular distance. Okay, so this is perpendicular. It can't be like over here. It has to be perpendicular to the sides of that angle. Get rid of that. All right, so how do we know this? Well, let's think about what we do. If I'm trying to show that those blue lines are congruent, and I don't know that yet, let's look at what we do know. We do know that, here I'll even unmark them, congruent. We do know that these angles have to be right angles, and we already know that these angles are congruent, so we already have two angles, and then this side that they share in between, that's reflexive, so it's congruent by reflexive property, so we have angle, angle, side. Angle, angle, side shows that those two triangles are congruent, so by CP/CTC, we know that these two lengths right here have to be congruent. All right, so that's our angle bisector theorem. Now, of course, we're going to have the converse of that. And so what that says is if I know a point is equidistant to the sides of an angle, then I know that point has to be on the angle bisector. So this ray that this is on has to be an angle bisector. So these would have to be congruent. So that's kind of going backwards. So again, if I don't know that these two angles are congruent, why would I know that this is true? So let's see what we've got. We've got these right angles, which we know are congruent. We have these sides of the triangle, and again, we have that reflexive property of that side in the middle. So no, we can't use angle, side, side. However, this is a special right triangle. It's a right triangle, not a special one, but then we can use HL. So even though we can't use angle, side, side, we can use HL in this situation. So by CP/CTC, we know that those angles are congruent. All right, so let's apply this. All right, so if I'm in this diagram right here, notice that I know that this point is equidistant to the sides of that angle. So that means that these two angles are congruent. So angle CBE has to be 31 degrees. All right, in this other one, we want to know what value of x does P lie on the, or what values of x does P lie on the bisector of angle J? So we want P to be on this angle bisector. So if that's an angle bisector, then what has to be true about these two lengths? Well, they really didn't tell us that these were the exact distances. So I'm gonna assume that on this one, but normally they would have to give that to us. So we would have to know that those two are congruent, and we would say x plus 1 is equal to 2x minus 5. And then we would just solve. So I'm going to subtract the x and add the 5. So we would say for x equals 6, then P lies on the angle bisector of J. All right, so now let's talk about what do we have if we have multiple angle bisectors. We're going to talk about concurrency again. So remember, concurrency is when we have 3 or more. Okay, so the angle bisector of a triangle intersect at a point equidistant from the sides of the triangle. This point of concurrency is called the incenter. All right, so again, this point where all of the red lines are the angle bisectors. Okay, so we have these. Those are the angle bisectors. And the point where all of those meet is going to be the incenter. Incenter is the center of a circle that is inscribed in this triangle. So it would be, if I could draw a circle really nicely, I know it's kind of lopsided the way I drew it, but I would be able to have a circle that touches all the sides of this triangle. So where those sides touch, those are what they're calling the distance from this incenter to the sides. Notice that these are perpendicular. Also notice that these blue lines are not the perpendicular bisectors, okay? So this distance over here is not the same as this, so be careful with that, okay? It's just going straight from this in-center perpendicular to the sides. So all of those, again, since those are the radii of the circle, the in-center, those are going to be congruent to each other. And that's what our theorem says. The concurrency of an angle bisector of a triangle, they intersect at a point that is equidistant from the sides. All right, so we're talking about these blue lines being congruent to each other. All right, and they say this is another way of saying it over here. Okay, so let's use this information to help us in this diagram. So in this diagram, G is the in-center. Okay, so G is the in-center. That means all of these are angle bisectors. Okay, and then they want us to find GW. Okay, so GW is right here. So notice GW goes from the in-center perpendicular to one of the sides. So that is actually what we've been talking about. We said that all of these should be congruent to each other. So we just need to know what one of them is in order to know what GW is. Now it might be confusing, but when they're labeling this side right here is 13, and this side right here is 12. So we need to use that to help us figure out what this GU is. Notice that makes a triangle though, a right triangle. Pardon me. So so what can we use to find the third side of that right triangle? Pythagorean theorem. Right, so we'll call this x. So x squared plus 12 squared equals 13 squared. And then if we subtract that, we're going to get 25. So x equals 5. You might have also noticed that this is a Pythagorean triple, a 5, 12, 13 triangle. So if this is 5, then GW is also 5. All right, so we use that in center to help us figure out that segment length. All right, so see if you can figure out what to do with this one. All right, we have the angle bisectors meet at point W. And they want us to find the value of D. All right, notice D, they're labeling these distances to the sides of the triangle. So these should all be congruent. So my setup should be 2D plus 7 equals 4D minus 1. All right, so if we solve that, subtract the 2D, add the 1, and we get D equals 4. Is that what they wanted us to find? Yes. So we're finished with that one. All right, just a few more just to test yourself. All right, we've got the perpendicular bisectors. Okay, so remember, they all meet at point D. These are the perpendicular bisectors. Okay. These are, the blue lines are not congruent, right? The distance to the vertices are what's congruent. So the red lines should be congruent. All right, they want us to find GC. So since this was 7 right here, GC will also be 7. All right, and then over here, we have the angle bisectors. All right, so the blue lines are the angle bisectors. The blue lines are not congruent. Remember, the lengths to the sides from the in-center are congruent. All right, so they want us to find MK. That will be congruent to the other red line. So MJ was labeled as 5, so MK will be 5. All right, so make sure you get those straight in your head. And then when we come in for class, be ready to go and have your notes ready. Okay.